Hello, my name is Sinwoo Kim, and this is my lab report for Lab 2, Magnetic Field of a Bar Magnet. This report will consist of the introduction, principles, experiment, coding, results and discussion, and a conclusion. The purpose of this lab is to observe the distance dependence of a magnetic field from a bar magnet and compare the observed versus expected magnetic field at a certain distance away at 45 degrees. For the results, I got that n in the distance dependence formula equals negative 2.9411 and the magnetic dipole moment is 2.947. Also, the observed magnitude for my experiment was 3.6316 times 10 to the negative 5 Tesla, and my expected magnitude for my computational model was 3.027 times 10 to the negative 5 Tesla. The key principles we'll be looking at today include the Biot-Savart law, which describes the magnetic field produced by a steady electrical current, the magnetic field of a dipole, aka our bar magnet, and the distance dependence formula of the magnetic field of a bar magnet, and next to it is the linearization of that equation. In this experiment, I used a magnetometer app on my phone and first compensated for Earth's magnetic north and created an x-axis from west to east. Then I located my magnetometer chip and measured the distance at which the bar magnet caused net magnetic fields of certain magnitudes, both on and off axis. The system is my magnetometer, and the surroundings are the bar magnet and the entire Earth. These are my measurements that I received from my on-axis experiment, where I focused on the net magnetic field on the x component, and then to the right is the linearized equation of the distance dependence formula so I could plot this line. Using the line slope-intercept formula and the distance dependence formula that was linearized, we can find that n is equal to negative 2.9411, which is my slope. These are my measurements for the off-axis part of the experiment, where I focused on the x, y, and z components of the magnetic fields, and I corrected it according to Earth's magnetic field. These are the two observations I made. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. These are consistent with the distance dependence formula, and using the natural log of k from my slope-intercept formula in the previous slide, I can rearrange the distance dependence formula to find the magnetic dipole moment of the bar magnet, which was 2.947. These are the conditions for my computational model, where I have set the constant mu naught over 4 pi, created the magnet at the origin, and set my measured magnetic dipole moment mu. I also created a function to calculate the magnetic field of a dipole for me, and set 6 different observation locations, 2 on-axis and 4 off-axis. Here's the rest of my code. Firstly, I calculated and drew an arrow to represent the magnetic field on axis at those 2 observation locations, and then I calculated and made arrows for the 4 locations perpendicular to the axis to represent the magnetic field. To the right, you can also see that I made an arrow to calculate and depict the magnetic field 45 degrees off axis. Here is the output for my computational model, and the arrows help us visualize the magnetic field of our bar magnet. The assumptions here are that the bar magnet acts as a magnetic dipole, and the magnetic field's strength depends on the distance away from the bar magnet. To the right are all the values that have been calculated for me, and in particular we're looking at the magnitude of the magnetic field at a 45-degree angle at a distance d, and d is given above, and the magnitude was 3.027 times 10 to the negative 5, which is our expected value, and our observed one that was shown in my measurements earlier is 3.6316 times 10 to the negative 5. So they are very close, but there's still a bit of a difference. Therefore, we need to cover 2 possible sources of error. First, external magnetic fields, like electronics, may be present and interfere with our measurements. Also, the location and angle of the magnetometer can easily fluctuate and be inaccurate. Here are some what-if questions. What if we did not orient our setup to compensate for magnetic north and instead laid out our meter stick at some intermediate angle? The Earth's magnetic field would have interfered with our magnet's magnetic field, and the measurements would be completely different and a lot harder to understand. What if instead we used 2 identical magnets stuck together end to end instead of our single magnet? How would our measurements differ? The magnitude of our magnetic field would double, but its direction would always remain the same because they are still end to end.